Good morning, friends. Last we discussed about the different spectral series for hydrogen atom, like as the Lyman series, Balmer series, Parsons, Beckett, and Font series. Right? Okay. Now, this type of the series is obtained due to the transition of an electron from different energy state to the either n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and n is equal to 5 energy state. Right? Okay. Now, in figure, how the electron make the transition, or during the transition of electron from any orbit to the any orbit, which type of the spectral line is obtained. Today we are going to discuss this thing. So this question is only informative. We must be familiar with that, the transition of electron from one orbit to the another orbit on the base of the orbit, and also on the base of the energy level. We are going to discuss this thing. Whatever the wavelength or whatever the spectral series is obtained during the transition of electron. Okay, now the question is that explain line spectral diagram for transition of an electron between energy level in an atom. Actually, this is for the hydrogen atom. Now we know the equation of wavelength or the wave number of light emitted during the transition of electron from higher energy state Ni to the lower energy state Nf, here the Ni is greater than Nf. The equation of the wavelength or equation of the wave number 1 upon lambda IF is equal to R into 1 upon Nf square minus 1 upon Ni square. Here the condition is that Ni must be greater than the Nf. That is the equation of wavelength or wave number. Again, the equation of the wavelength or the wave number of light emitted during the transition of an electron from the energy state Ni to the energy state Nf, here the Ni is greater than Nf. That means the energy of Ni state is much more than the energy of energy state Nf. Okay. So this equation is 1 upon lambda IF is equal to R into 1 upon Nf square minus 1 upon Ni square. Here condition is this, Ni must be greater than Nf. Okay. The spectral line from all different transition of electron in hydrogen atom is shown in the figure. Right? Okay. So there is the energy level, n is equal to 1, n is equal to 2, 3, 4, and so on. There is the ground state. There is the ground state, and these are the excited state already we discussed. There is the first excited state, second excited, third excited. When the electron make the transition from any orbit or the energy state to the any energy state to the ground state, or the n is equal to first energy state. Due to the energy difference, the photon having the energy difference between these two energy states is emitted. The wavelength of this photon is fall in the Lyman series. So there is shown electron make the transition from second orbit to the first orbit, third orbit to the first, fourth orbit to the first, fifth orbit to the first, and corresponding H alpha line, H beta line, H gamma line, H delta line are obtained. Clear? So these are the spectral line of the Lyman series corresponding to the different transition of an electron from 2, 3, 4 orbit to the ground state, or the n is equal to first energy state. Similarly, the electron make the transition from any orbit to the second orbit or the first excited state. What are the photon emitted? The wavelength of this photon is found in Balmer series, and corresponding to the transition of an electron from 3 to 2, 4 to 2, 5 to 2, H alpha, H beta, and H gamma line of the Balmer cells are obtained. The similar way, when the electron makes the transition from any orbit to the third orbit or second excited state, the photon with the wavelength emitted is fall in the Passon cells. And also we obtain the H alpha, H beta, H gamma and H delta line of this spectral cells. And when the electron makes the transition from any orbit to the fourth orbit, the photon emitted with the wavelength fall in bracket cells. And also corresponding H alpha, H beta, H gamma, H delta line are also obtained for the bracket cells. And the same way, when the electron makes the transition from any energy state or any orbit to the fifth orbit, the radiation with the wavelength fall in the front cells. Now, the Lyman cells is in ultraviolet region, Balmer cells is in visible region, while the Passon, Beckett and front cells are in infrared region of electromagnetic spectrum. So here we write down like this way: if in this equation Nf is equal to 1 and Ni is greater than 1, that means the 2, 3, 4, 5 and so on. Right? The wavelength of the light emitted or the spectral line H alpha, H beta, H gamma, H delta of the Lyman cells are okay. Like this way, if Nf is equal to 1 and Ni is equal to 2, 3, 4 and so on, the spectral line H alpha, H beta, H gamma and H delta are obtained. Of Lyman cells. Because the general equation for the Lyman cells is that 1 upon lambda is equal to R into bracket 1 upon 1 square minus 1 upon n square. N has the value is 2, 3, 4. Therefore, whatever the wave number of the wavelength is obtained, that fall in the Lyman cells. The similar way, if Nf is equal to 2 and Ni is equal to 3, 4, 5 and so on, the spectral lines like as the H alpha, H beta, H gamma, H delta, etc. of Balmer cells are obtained. And similarly, third is the Passon cells. If Nf is equal to 3 and Ni is equal to 4, 5, 6 and so on. 4, 5, 6 and so on. The spectral line H alpha, H beta, H gamma are of Passon cells are obtained. And if Nf is equal to 4 and Ni is equal to 5, 6, 7 and so on, the spectral line H alpha, H beta, H gamma, H delta, etc. of Physcis are obtained. And similarly, if n is equal to 5, nf is equal to 5 and ni is equal to 6, 7, 8, 12, the spectral line H alpha, H beta, H gamma, etc. of point stays obtained. So that is the diagram from the energy level, and it is shown in the orbit. So the central small region is known as the nucleus, having the positive charge. The first is the ground state corresponding to the n is equal to 1, and other orbits are known as the excited state corresponding to the n is equal to 2, 3, 4 and so on. When the electron makes the transition from second to the first, that means any orbit to the ground, third to the first, fourth to the first. So the wavelength of the light emitted during this transition is told in Lyman cells, or the Lyman cells is obtained, and corresponding to the 2 to 1 is alpha line, 3 to 1 transition is beta line, 4 to 1 is gamma line, 5 to 1 that is the H delta line are obtained. Right? The similar way, from any orbit to the second orbit, the electron makes the transition. The wavelength of the light emitted is in Balmer cells. That means in visible region. And when the electron makes the transition from any orbit to the third orbit, so the wavelength of the light emitted by this transition is called in Paschen cells, or the Paschen spectral cells is obtained. Similar way, in hydrogen atom, if the electron makes the transition from any orbit to the fourth orbit, so the wavelength of the light obtained is told in Beckett cells. And then last is, if the electron makes the transition from any orbit to the fifth orbit, so the wavelength of the light emitted by during this transition is in third cells. So that is the basic information how the spectral cells are obtained during the transition, different transition of an electron in hydrogen atom on the base of the energy level and also on the base of orbits. So keep in mind these two figures so we can visualize in our mind each and every time what is the Lyman cells, what is the Balmer, what is the Paschen, Beckett and also the point cells. And general equation for the spectral line is 1 upon lambda IF is equal to R into 1 upon m square minus 1 upon n square, or 1 upon lambda IF is equal to R into Beckett 1 upon nf square minus 1 upon ni square. For different value of nf, we obtain the different spectral cells. And as we take the different value of ni, we obtain the different spectral line. Like as the alpha line, beta line, gamma line, delta line for different cells. Clear? Oh. Okay, now friends, what is the quantization of an angular momentum? Right. Rutherford already suggested the atomic model, but Rutherford cannot explain, whether Rutherford's atomic model cannot explain the stability of an atom. So in those cases, the Niels Bohr suggested the three hypotheses to explain the stability of an electron. So in Bohr's atomic model, our question is that explain the quantization of angular momentum, or to behave an electron as a wave in atoms. How the electron behaves as a wave in atom during the transition of an electron from one orbit to the another orbit. Right? Okay. In Bohr's atomic model, the Bohr combined the quantum concept and classical concept and suggested the three hypotheses. In Bohr's atomic model, the second hypothesis suggests that the angular momentum of an electron orbiting around the nucleus is quantized. What is the second hypothesis in Bohr's atomic model? Out of numbers of the orbit around the nucleus, the electron can revolve only in those orbits for which its angular momentum is integral multiple of h upon 2 pi. That means n is the integer value 1, 2, 3, 4 and so on. So out of these numbers of the orbit, the electron can revolve only in those orbits for which its angular momentum must be integral multiple of h upon 2 pi. Right? So here we are going to discuss this, the wave nature and particle nature of electron according to the de Broglie's wavelength, and also how the angular momentum of an electron in particular orbit is quantized. So in Bohr's atomic model, the second hypothesis suggested that the angular momentum of an electron orbiting around the nucleus is quantized. Now, Bohr proposed that the electron in a circular orbit should be as a matter wave. That means the Bohr suggested that when the electron is orbiting around the nucleus, during this condition, it behaves as a matter wave. How it? For that purpose, the one example is that already we discussed in 11th standard, the wave. What is the wave? First thing, the disturbance propagated in a medium is known as the wave. We also discussed about that the wave produced in a string. So there is the string tied at the both end, or the both end of the string are fixed. Yes, the disturbance is produced at any point. So what's happened? The waves are generated and propagated in both directions. Right? So there is the incident wave and reflected wave are also produced having the phase difference of 180 degree. There is the reflected wave. And that is the incident wave. Already we discussed in 11th standard last chapter. The phase difference between the incident and reflected wave is 180 degree. Here we have first take the one example of the wave produced in a string. When a string is plucked, a number of waves are excited. On those waves survive which have the nodes at the end of n. What is the node and antinode of a wave? There is the wave. What is the node and antinode? These points are known as the node. And these points are known as the the antinodes. As the antinodes. So antinodes are these. So as the disturbance produced in a string, the number of waves are produced in a string. Out of these waves, only those waves are shown in the string which has the node is at the end of a string. That means there is the end of a string. The wave with this node is coincide with the end of the string are only produced the stationary wave. While the other waves are totally absorbed by the rigid support. So here, all those waves survive which have the nodes at the ends and form a standing wave in the string. So first our concept about this must be clear. when the string is plucked, that means the disturbance is produced in a string and the burst of the waves are produced. Out of these waves, only those waves survive which have the nodes at the end of the string and form a standing wave in the string. It means that in string, the standing waves are formed when the total distance traveled by the wave down the string and back in one wavelength or the two wavelength or any integer multiple of the wavelength. So what is the meaning of this? When the nodes of any wave is coincide with or the incident at the end of a string only produce the standing wave or the stationary wave in a string. So meaning is that in a string the standing wave are formed when the total distance traveled by the wave on the string and back is equal to the either the one wavelength or the two wavelength or integer multiple of the wavelength. If the distance traveled by the wave is equal to the integer multiple of the wavelength, either 1 lambda, 2 lambda, 3 lambda, or as same as the n lambda. When the distance traveled by the wave during the incidence and reflect back, this distance is equal to the either lambda, 2 lambda, 3 lambda, or n lambda. So only those waves are survive or produce the stationary wave in a string. Using this concept for an electron moving in the nth orbit of radius I, the total distance is the circumference of the orbit. Now the one electron, that is the nucleus, electron is moving on the nth orbit and the radius is I. If the total distance traveled by the electron is equal to the circumference of the orbit is equal to the integer multiple of wavelength corresponding to its wave nature. Again, if the electron revolves or the orbiting around the nucleus in nth orbit and the radius is I, the total distance traveled by the electron during the one rotation is equal to the circumference of orbit. If this distance is equal to the integer multiple of wavelength of an electron due to its wave nature, at that time the stationary waves are produced in this orbit. Therefore, the circumference of orbit is equal to n times wavelength. Circumference of orbit, nth orbit, and the radius is I, is 2 pi Rn is equal to n times lambda. That is our equation 1. Again, for an electron moving in nth orbit of radius I, the total distance traveled by the electron during the one rotation is the circumference of the orbit. Therefore, circumference of orbit is equal to n times wavelength. Therefore, circumference of the orbit 2 pi Rn is equal to n lambda. That is our equation 1. Here the n is equal to 1, 2, 3 integer value. Now, the relation of the de Broglie wavelength and momentum. Lambda is equal to h upon p. P is the momentum of an electron revolving or the orbiting in nth orbit. The mass of the electron is m and its linear speed in during the rotation is vn. Therefore, lambda is equal to h upon p is equal to h upon mvn. Vn is the linear velocity of an electron in nth orbit. Okay. Substitute this value of lambda in equation 1. Equation 1 is 2 pi Rn is equal to n lambda. So n into, instead of the lambda, h upon mvn. H upon mvn. Take this 2 pi on RHS and mvn on LHS. Therefore, mvni is equal to nh upon 2 pi. Now, mvn into I, angular momentum, is equal to n into h upon 2 pi. Thus, the angular momentum is integral multiple of h upon 2 pi. Is the second hypothesis of Bohr's atomic model. Which is the second hypothesis of Bohr's atomic model. Thus, the momentum is always integral multiple of h upon 2 pi. The quantized orbits and the energy state are due to the wave nature of electron, and only resonant standing waves can persist. Again, when the electron moving in nth orbit of radius Ra, the total distance is the circumference of the orbit. Therefore, the circumference of the orbit 2 pi I is equal to n times wavelength. That means the n lambda. Here the figure shows that when the electron evolves in nth orbit of radius R. So here the complete wavelength, or the wavelength must be integral multiple of n times wavelength. So this distance is known as the one wavelength. So there is the second wavelength, third, fourth. So figure shows the standing wave at the circular orbit for 4 wavelengths. The total distance is 4 times wavelength, 1 times, 2 times, 3 times, and 4 times. Right? So the relation of the d Bernoulli wavelength and momentum, lambda is equal to h upon t. Momentum, linear momentum of an electron, mass into velocity of an electron. Here the electron evolves in nth orbit of radius r. So its linear velocity or the linear speed is v. Therefore, lambda is equal to h upon mvn. Substitute this value of lambda in equation 1 is 2 pi I is equal to n lambda, that means the n into h upon mvn. Take the mvn on LHS and 2 pi on IHS. Therefore, mvn into I is equal to nh upon 2 pi. That means the angular momentum of an electron is equal to integer multiple of h upon 2 pi is the second hypothesis of Bohr's atomic model. Right? Thus, the angular momentum of an electron is quantized. Right? The quantized orbit and energy states are due to the wave nature of an electron. And the only resonant standing waves can persist. Clear? There is the quantization of an angular momentum. Clear?